Welcome to this short introduction on the core concepts of network embedding. The goal of embedding is to represent networks, including biological networks such as protein interaction networks, in a manner that makes them convenient, for example, when you want to apply machine learning. This video requires a bit of background knowledge. If you don't know already what nodes and edges are, I strongly recommend that you go watch my network biology video first. And if you don't know the difference between unsupervised and supervised learning, I strongly recommend that you watch my video on machine learning first. In this video, I'll go over what's the problem with networks in the context of machine learning, what is the idea of embedding, I'll talk about specifically the node-to-vec algorithm, how you can evaluate the quality of an embedding, and finally go over a couple of concrete use cases that we've used them for. So what's the problem with networks? Well, if you want to do supervised learning, you generally want to have a feature vector that represents each of your examples that you're trying to make predictions for. If you're working with sequences or images, these are relatively easy to represent, and a big part of the reason is that the letters are ordered within a sequence and the pixels are ordered within an image. Meanwhile, networks are a lot harder to represent, and a big part of the problem is that the nodes within a network are unordered. We thus need to come up with some way of getting vectors for nodes, and we want them to behave in a manner so that the similarity of the vectors captures the distances within a network. What does that mean? If you're looking at the network on the left, you want to get vectors like you see on the right. You want the vectors to be so that nodes that are near each other in the network are similar in your vector representation. This is what we call a network embedding. How do we create an embedding from a network? There are several algorithms. The one I'll focus on here is called node-to-vec. It's the most popular one and is the one we've been using. The basis of it is random walks. If we look at the network from before, we can pick a random node, A, and do a walk through the network and thereby produce this sequence or sentence. If I pick another starting node, I can create another sequence or sentence. And I can make a whole collection like this. If you look at these, they are network sentences in which the nodes are effectively your words if you want to make the analogy in language. Nodes that are near each other are going to have similar sentence contexts because you make them by walking the graph. We can now steal a technique from text mining called word-to-vec, which is used to create vectors for words, and since our words are nodes, we are now going to get vectors coming out of all these different nodes in our network, and thereby we're getting our network embedding as we want it. The next thing you need to worry about is how to evaluate your embedding. You need to be able to assess embedding quality in order to pick the right algorithm and choose the hyperparameters so that you can obtain the best possible embedding. The typical way of doing this is to look at network reconstruction. You hold out some edges, effectively a test set, and then you create an embedding, train it on what remains of the network. You can then calculate vector similarity for your test examples, and that way predict held out edges based on similarity in your embedding space. You can then go and calculate your typical performance metrics such as the area under RUG curve, and that way measure the inherent quality of your embedding. One problem with this that you need to be aware of is that it completely ignores the dimensionality of the embedding. And for that reason, it may be suboptimal for your task. It may be that the best set of hyperparameters gives you a very high dimensional embedding, but that may not be what you want for a downstream task. So for that reason, you typically want to do downstream evaluation afterwards and try to use, for example, your embedding input vectors for a supervised learning task. This means you have nodes that have now been labeled, not based on the network, based on something you want to predict from the network, and you now test thereby the utility of your embedding at solving the task. Let's get a bit more specific and look at some concrete use cases. Here I'll talk about protein embeddings created from the functional associations in the string database, thereby creating embeddings that capture biological systems. While still at the Novo Nordisk Foundation Center for Protein Research, we developed SPACE, string proteins as complementary embeddings. This resource provides both network embeddings and sequence embeddings for all eukaryotic proteins in the string database. We tested them on 2 different multi-label classification tasks, specifically prediction of subcellular localization and prediction of gene ontology terms. We tested the performance on published benchmarks, and that allowed us to compare it to other existing methods. And what we saw was that we were able to get state-of-the-art performance or near state-of-the-art performance on these tasks by just putting a simple logistic regression on top of the embeddings. That tells a lot about the quality of the underlying embeddings. Since moving to ZS, we tried using the same approach, now focusing on human string embeddings, to make molecular disease maps starting from multi-omics data. We use the following workflow for it. The string network provides our feature vectors through Node2Vec, whereas disease-specific omics data allow us to do protein labeling in terms of proteins that are relevant or not relevant to a disease in question. We can then train a classifier on top of that, predict which proteins are relevant for the disease given the network embeddings, and then do all kinds of network visualization and investigation afterwards, as well as benchmark the performance on what is known about the disease mined out of literature using text mining techniques. We tested the approach on 7 different diseases, and we generally see 2 to 4 times better sensitivity at the same specificity compared to what we get out of just using the omics data alone. This shows that the networks are really a great starting point for doing things such as target discovery. I hope you found this video interesting. If you did, I suggest you take a look at this playlist, which covers many other different aspects of biological network analysis. Thanks for your attention.